So
Yes.
I will just go to the last. Okay, so welcome everyone. As Vinicius told, my name is Joanna Godzin, and for many, many years I was working at Professor Coral Barba's lab at San Pablo Seu University. During this time, I met Vinicius. We were working there together. Now I'm back in Poland, working at a Clinical Research Center of Medical University of Białystok. Although I changed the place, still my main interest in terms of untargeted metabolomics and lipidomics is metabolite annotation. And today I would like to share with you some of my thoughts, some of my ideas and observations related to the annotation of lipids. So let's start. Just to control, I will put the timer on. Okay, so in general, the idea behind performing untargeted research is to measure molecules with a different structures to assign later those structures to the different functions, different biological properties. The idea is very simple. We do believe that behind particular chemical structure, either if this is a linear structure of molecule containing some rings, depends on the functional groups that are there. Particular molecules, particular metabolites will have very precisely defined properties, and those properties later will affect the function those metabolites or those lipids serve in our bodies, in our organism. Measuring the different properties of the molecules present in biofluids, such as plasma, serum, urine, or extracts from different tissues, the idea is that we can assign those measured properties to the structure, particular structure to particular metabolite, and finally particular metabolite to particular function. And based on those information, we can later connect observed changes on the level of metabolites or lipids to the phenotypic changes that we observe in a given disease or disorder. Today, I would like to talk about lipids. Everyone who is working with untargeted studies for sure observe in plenty of different projects lipids. And they are involved in many different biological pathways, in many processes, and because of this, we measure them almost in each and every project, in each and every sample. There is a very big debate about defining indeed what the lipids are. And today I don't want to go into too precise definition of lipids. I will follow mostly the definitions and classifications provided by lipid maps, but I just want you to be aware that depends how we define lipids. This group of molecules can be corresponds to the wider or narrower group of molecules. But still, lipids themselves are very, very broad and group of molecules with many different properties. Talking about the lipids, and especially about lipids identification, we have to start from the building block concept. These concepts are really really simple. Maybe easy, it's not a correct word, but really simple, and they allow us to understand different lipid classes, different lipid properties, and also later how those lipids behave from analytical perspective. And the idea, the concept of building blocks basically refers to an idea that they are some basic parts, basic bits of the molecule to which we will attach different blocks, and depends what are those attached blocks, we will create other phospholipids or glycerolipids or glycerophospholipids. So following this idea, we can classify the lipids, and later we can quite easily predict their fragmentation and let's say analytical behavior. Those building blocks are very precisely described in the literature, and you can find many different publications related to this topic, where you can find a whole list of different functional group, different chains that can be attached to each side here, and therefore forming one or another group of lipids. We can go here either from very broad lipid classification, like we can just say that this is glycerolipid, glycerophospholipids, or sphingolipids, or depends on how detailed will be information about those attached building blocks. We can provide really precise information about some lipids, including the position of double bonds, the presence of some particular functional groups, even starting from hydroxyl groups, or some more complex attachments, such as different kind of sugar modifiers for glycolipids. Depends on different properties of lipids, we can classify them in a very, very different ways. You can find in the literature dozens, literally dozens of different classifications, depends which properties of lipids we will consider. And today I would like to stick to the classification provided by lipid maps. And that will be the classification that I will follow. But as I told, there is no one single classification. You can find many of them. Why lipid maps? First of all, lipid maps, it's conducted considering lipidomics and untargeted studies. And also this is an initiative that it's still alive, let's say, that the work over this platform, it's still ongoing, that the classification, it's still updated, and the new updates frequently are published. So I highly encourage anyone who is working with lipids to get familiar with this platform, to stick to the nomenclature provided by this platform, as well as the classification. And we can see here 8 main lipid categories, which can be further subcategorized to classes and subclasses, with examples given for each and every class. And as I told, frequently every 2-3 years there is an update on classification. New classes are added because, for example, new lipids were discovered. So this is very important, that this is not something given once forever, and it's not following, in fact, what is going on in the field, but all the needs of the field are reflected in this platform. That's why I highly recommend to use it and encourage everyone to follow these classifications. Also, in terms of the nomenclature and how to present the lipids, but about this I will talk with more details in a few minutes. So in general, we measuring our lipids or metabolites, we can acquire a different characteristics. We can measure a different parameters, depends what is the equipment that we have. We can having ion mobility, we can get cross sections. Performing chromatography, we will have retention time. We can have either only MZ if we are just performing MS scan measurement, or we can also have fragmentation spectrum, which can provide us information about the structure of the molecule. And at this point, I know that those of you who listen to some of my previous talks knows already very well this difference, but I think it's very crucial to know the difference between identification and annotation. That's why, as long as I will be giving talks about identification, I will be mentioning these two terms. In the literature, these two definitions are used interchangeably, which is not correct. Why? Because identification, by the definition, is a process in which we are assigning some metabolite ID into our measured ion based on the authentic standard. So we already have some idea about what our metabolite, what our lipid might be. We are purchasing the standard. We are analyzing this standard under identical conditions to those that we use to measure our samples. And then we are comparing the measured properties of this authentic standard with measured properties of our ion. And if at least two orthogonal properties are the same, we can assume that we identified particular lipid. This term orthogonal characteristics is also very important, because that refers to the fact that in the identification process we should use information from different sources. What that mean from a practical point of view? We cannot use for the identification only the mass matching and MS/MS fragmentation matching, because both MS information and MS/MS information came from the mass spec. And so we have to use, for example, MS/MS fragmentation pattern and retention time, because MS/MS came from the mass spec and retention time came from HPLC. We can combine retention time information and CCS from the ion mobility, and more orthogonal characteristics we will put together, higher confidence of identification we will achieve. Another term that is very important is annotation. To annotate something means to compare the properties of a particular ion that we are trying to annotate with libraries, with databases, with something that it's not originating from an authentic standard. So I can compare in this process, for example, my own MS/MS fragmentation spectrum with the MS/MS fragmentation spectrum from, let's say, methylene. Or I can compare, I can try to elucidate the structure based on the obtained fragments of obtained product ions. I can try to predict what will be the structure. That will be annotation. So in a majority of the cases, when we are saying that we are identifying metabolites, in majority of the cases, we are annotating them. Why? Simply because the number of commercially available standards is highly limited. And this problem is even bigger in terms of lipids, because the number of commercially available lipids is really little in comparison to the lipidome coverage, to the number of lipids that indeed we can find in the biological matrices. So today I will be, in majority of the cases, I will be referring to the annotation, not identification process. I already mentioned that depends on which properties we will use for the identification or annotation, we can reach a different confidence level. And this is also something that I'm mentioning quite often, but I'm doing this because I really deeply and truly believe that this is extremely important in the annotation process, extremely important while reporting our results, and extremely important to really compare the data, the results provided by different research centers. So here, there are several different systems classification to report confidence confidence level in the annotation. However, I limited them only to two most frequently used, and in my opinion, the best. The first one, it's historically the first classification that was provided. It was already in 2007, and Metabolomics Society, it's behind this initiative. At the beginning, this classification started from the level 1 and finished on level 4. In 2018, it was updated, adding also level 0. There is another classification provided in 2016, where we have 5 confidence levels. In both classifications, the lowest level of confidence is given for unknown. So we can report an unknown in our publication, but it has to be clearly stated that it is an unknown. And in one classification will be level 4, in another level 5. Then we have level 3, which corresponds to the level 4 in this classification, which corresponds to just putatively characterized compounds. We can only say what is, for example, a chemical formula based on the isotopic distribution, what is the charge, what is the adduct, and maybe based on some information, if we are really experienced in annotation, we can also say which group of metabolites in general this might be. Then we have a level 2 of annotated, putatively annotated metabolites based either on MZ matching or MS fragmentation, which in the second classification was divided into 2 separate levels. Level 3, where we are just tentatively annotating metabolites based on MZ matching, and putative annotation based on MS fragmentation. In my personal opinion, the separation of these 2 levels makes a lot of sense, because in my opinion it's highly unfair to put on one level, on one line, MZ matching and MS fragmentation, because obviously the second one gives much higher confidence in the annotation, and it's quite unfair to assign to both of these methods to the same level. Level 1 in both cases corresponds to identification. So in both cases we are talking about the comparison of measured properties with the standard. And in terms of this first classification, we have also level 0, which it's rather reported for some studies based on, rather for plant metabolomics, where some compounds are isolated, purified, and different properties of those isolated and purified compounds are determined, including also really precise structure determination based on NMR, yeah. In terms of metabolomic studies, this level 0, in terms of, I don't know, human studies, it's really not so common. So it doesn't matter which classification we like more or which we prefer to use. In my opinion, it's really important to use them. And if we are reporting our tables with the list of identified metabolites that are statistically different between 2 compared groups, we should also add a column confidence level and just write 1, 2, 3, 4, 5, whatever. Keep in mind that in one single table you can put metabolites and lipids annotated with very different confidence levels. It's not says that only level 2 is accepted. No, we can put different levels, but we have to clearly define what is the level of confidence, how we annotated particular molecule, because maybe there are other candidates, maybe we didn't consider that there might be an alternative annotation, and maybe because of this our results doesn't make sense when we are comparing them with results obtained by someone else. If we would put this clear information, clear indication in our publications, I really believe that that will change, that will improve our scientific life. So I encourage everyone to choose one classification and to start to report the results, to publish using these classifications. So as I mentioned, depends what is the level of confidence. We first of all can trust more or trust less our annotations, but also going up with the levels of confidence. Also, we can provide more details about the structure. We can name our compound more precisely. And as you can see of this scheme, provided by Emma Szymański, putting on the table information from different sources as MS, MS, retention time, and so on, we can increase the confidence of our annotation. And what is really important is that even if we will use the best available on the market mass spectrometer with the highest resolution, with the best accuracy, still this is not enough for really confident annotation, and we must look for orthogonal information. And today, with some examples, I will try to show you that this is not just one-way process. It's not that we will find a candidate, then check MS structure, then confirm with retention time, and goodbye, it's done. No, this annotation process, sometimes this is the process of going back and forward. I have some information based on MS level. I have to go back to MS level. Then maybe I have to check the retention time information. Then with this data, I have to go back again to MS. So this is like a going back in their process, and it's really, I'm sorry. And it's really important to, first of all, have this orthogonal information, and second of all, to really make use of this information and put all the available information on the table. Today, during my talk, I will mostly, but not only, refer to reverse phase LC MS, including MS data with electrospray ionization as an ionization source. So starting from the ionization, the idea behind using electrospray ionization is that we have our metabolites in the form of ions present in some aqueous phase, and once while this phase is reaching the ion source, the solvent is evaporated. Finally, in a few-step process, releasing charged ions to the gas phase, which are later entering the mass spectrometer and are measured. And thinking about ionization, very often we have this quite simple idea in our mind that we have either protonated forms in positive ion mode or the forms without hydrogen in negative ion mode. But the situation is a little bit more complex, because the molecules can form different kind of ions with different adducts. Majority of metabolites and lipids, I would say rather metabolites, maybe lipids not. In many cases, molecules can form just a single ion, which in positive ion mode it's a protonated form, but many of them, especially in terms of lipids, can form several different adducts with a different ions, forming different ions. And furthermore, formation of these ions, it's not by chance. It's not something that is happening randomly and unreproducibly. No, it's just the opposite. Majority of such cases can be very precisely described, and we can prepare a kind of preferred list of formed ions. So we will have, for example, protonated form as the main form, then followed by signal with sodium, and finally potassiated form. And as I told, this is not something happening randomly. I would rather say that it's highly conservative, and as long as we are not changing significantly the mobile phase, this pattern will be observed between different laboratories. Of course, it might happen that, for example, protonated forms, it's twice as high as sodiated in my lab, but only 1.5 times higher in another lab. But still, it will be significantly higher than sodiated form. So this is something I would say rather conservative. And for different classes of lipids, particularly, this is particularly important for lipids, we can use this information about different ions formation for annotation purposes. For example, phosphatidylcholines can be ionized by protonation, and that will be the main ion that they form, but they can also be ionized with sodium. But this will be never the only signal that they give. That will be never the only ion they form, but this ion must be observed after the protonated one, and therefore will be always less abundant than N+H. And the same in terms of potassiated form. We can observe potassiated phosphocholines, but they will be less abundant than sodiated and also protonated. In terms of triglycerides, if we add ammonia to the mobile phase, they will be very nicely detected with ammonium adduct, but they never form, never, this signal N+H protonated, it's that little that we can even say that they rather do not form this ion. In terms of phosphocolines in negative ion mode, if we add to our mobile phase formic acid, they will be ionized with formate, but never by deprotonation. Therefore, knowing how different lipid classes behave in terms of ionization and adduct formation, we can establish, define some rules that can be used in the annotation process. Here I brought an example of sphingomyelin that can form 3 different ions in positive ion mode. And when I look into my data, both on LC and MS level, I can nicely observe all of those ions. And what is highly important, I know that this is obvious, but I really prefer to pronounce this by loud, that if we are talking about ions formed by the same molecule, they must overlap. They must have exactly the same retention time, because ionization takes place after the chromatographic separation. So if each of these ions would give us a peak and different retention time, that means that we have 3 different lipids. But at the moment that all of them are at the same place, following the same peak shape, that means that most likely they correspond to the same molecule. Here I have example of 2 signals that were found to be statistically significant in one of my projects. I checked that both of them are very decent peaks. One of them more abundant than the other, but both of them looks very nice. I looked into the databases and I found that this one, MZ, might be LISO-PC with 16 carbons and 0 double bonds, and this one might be LISO-PC 18-3. So if I would stop at this moment, just sticking to the MZ matching, I would say, okay, 4 ppm error mass, it's acceptable. Here it's 0, fantastic. I would put to my table 2 LISO-PCs. But is this really true? Is this really correct identification? Even without MS spectrum, I can look a bit deeper into this annotation. What if I will add here information about the retention time? We can see then that both of these peaks have exactly the same retention time and very similar peak shape. And it's impossible that two different LISO-PCs will have exactly exactly the same retention time. Therefore, I went back to the databases, and what I found is that this second M over Z might correspond to lysopc16-0, but sodiated one. And the question is if those candidates make sense. And looking even only onto their abundance, yes, it's really reasonable, because protonated form is more abundant than sodiated one. They have the same retention time, so it makes sense. And indeed, later performing MS, I confirmed that both of these signals correspond to exactly the same molecule. So what is the message here is that even if we do not have very profound structural information about our lipids, let's try to make use of the data you have. So play with this data. You have only M over Z. Let's try to use information about adducts formation, and of course about the retention time. And here it's very nice example. I like to use this one. Here it's one MZ 518 measured in the positive ion mode. I looked into some candidates in the databases, and what I found is that it might be either, or if we consider that this is a protonated ion, some phosphocholines, or if we consider that it's a sodiated form, that there must be some phosphocholines or phosphoethanoloamines. Both candidates are equally possible, because we already know that phosphocholines can be ionized with sodium. So how to approach this? How to check what are our possible candidates? And one important thing, here on the list, I have only one candidate. I mean, it's lysopc18-3. Here I have PC and PE. What is important is that for each given phosphocholine, we can have phosphoethanolamine, because they have exactly the same chemical formula. The only difference will be the number of carbons in the fatty acid chain, which is always by 3 bigger for phosphoethanolamines. For phosphocholines, it's by 3 smaller, because 3 methyl groups are present in the choline head group. So let's go to the first candidate, that it might be just protonated phosphocholine, but I will also consider that it might be phosphoethanolamine. It's not in the database, but who told that? We know that not each and every lipid is in the databases. So both of them, phosphocholines and phosphoethanolamines, can be ionized through protonation. So this information cannot be used to decide about our identification. But what is important, in negative ion mode, phosphoethanolamines are perfectly detectable through deprotonation, while phosphocholines never form such ion. Instead, they are ionized forming an adduct with formate. So if I will recalculate MZs adequately for deprotonated and formated form, what I will see, with the red color, it's marked our protonated forms from positive ion mode, and I simply opened the file from negative ion mode, and I checked if there is MZ for deprotonated form. As we can see, there is no such signal, but I have a very clear, this brown signal corresponding to the formate adduct. I can see that there is a very slight retention time shift, but keep in mind that we are overlapping here a file acquired in positive and negative ion mode, so such a shift is understandable and acceptable. So with this information, I can conclude that this is rather not lyso-PE, but most likely lyso-PC, simply because there is no deprotonated ion. If that would be phosphoethanolamide, we should observe the signal in negative ion mode. We have another peak and another candidate. What about the sodiated form? If we assume that that might be either sodiated phosphocholine or phosphoethanolamine, we have to remember that we must observe also M+H signal, and this signal must be more abundant than sodiated one. So I just simply calculated the M over Z for protonated form. I created such a extracellular chromatogram, and as we can see, the black one that corresponds to the protonated form is much more abundant. I had to cut the signal at some point than the sodiated one. So in this way, we can say that this might be sodiated form, but it's equally possible that this is both sodiated phosphocholine and sodiated phosphoethanolamide. To decide either this is PC or PE, we have to go again to the negative ion mode. And we are following exactly the same reasoning as in the previous example. So the lack of the signal corresponding to the deprotonated form and the presence of really abundant signal corresponding to the formate adduct, it's telling us that rather this is phosphocholine, that phosphoethanolamine. Also from biological perspective, this choice makes more sense, because here we have even number of carbons and here odd, so this is easier to explain. Okay, so we created the list of such rules for different classes of lipids. Here we follow the classification provided by lipid maps, and we classified different ions to expected, what we expect, what is possible. So there is some condition to be met to accept some adducts, some ions, and which ions, which forms are rather impossible or not expected. We did that for positive ion mode, for negative ion mode. Different tables were created, depends what are the modifiers we use, because of course if we used formic acid, we will expect formate. If we use acetic acid, we will expect acetate, and so far and so on. So all these rules were implemented into Seumas mediator, and you can use them either through numerical score, where you search for your for candidates for your lipids, and the scores about the annotations will be given as a numbers, will be numerical score. Or there is also an application called LAS that will give you an explanation about the particular ions in the text, that it will be just explained in the text, either if it's possible or not possible, if particular annotation is expected or not expected, following the adduct or retention time information. Also, since as far as I remember, 2018, this functionality is available, accessible also through the HMDB. So I highly encourage you to try those functionalities. But keep in mind, because in the previous table we use classification from the lipid maps, those rules will be applied only to the lipids that are present in this database. Talking about different ions formation, I have to mention the problem of redundancies, which is especially common for lipids, and moreover those which carry some native charges, like phosphocholine. They have this fixed positive charge on the choline head group, and because of this they behave in a quite strange way in the ion source. And here you have just a snapshot of MS spectrum. This is MS, this MS1 level, scan level, and all marked ions, some of them really high abundant, dominating the spectrum, correspond to single molecule. And I can tell you that some champion molecules were forming even up to 18 different ions, both pulling together positive and negative ion mode. But as you can see here, among different ions form, we have also some fragmentation, in-source fragmentation. And in this way, I would like to focus for a moment on this phenomenon. So although electrospray ionization is a soft ionization way, and we believe that our molecules are ionized as an intact molecule, just forming some ions. The truth is that very often they undergo fragmentation in ion source, and later what we measure in our scans, it's despite the whole intact molecules, we have also their fragments. And this is not trivial problem. This is a very, very serious problem, which people are taking more and more seriously year by year, because only 10% of metabolites that are in methylene database do not dissociate in the source. So that means, let's read this other way around, 90% of the molecules dissociate in the source. So this is quite serious problem. And to illustrate this, I will bring example of 1M over Z, which based on the tentative annotation was assigned as a palmitic acid. But come on, palmitic acid cannot give that many peaks. It's impossible. It may be that one single molecule can give you 2 peaks if we are talking about some tautomerization, but not that many across more than 12 minutes over our chromatogram. So maybe this is the same M over Z, but we will have a different formulas. Let's see. So we checked the isotopy distribution for each and every of those peaks, and unfortunately all of them were exactly the same, and all of them were corresponding to the palmitic acid. Then we perform MS fragmentation for each of those signals, and we obtain the same fragmentation pattern for all of them. Of course, for the peaks that were less abundant, we were missing some of the smallest signals here, but in general, the fragmentation spectra were the same. So finally, we came to the point that it was time to use a commercial standard. We injected the pure palmitic acid, and what we found is that only this last most abundant peak corresponds to the standard. That the peak from the standard overlap with this last peak on our chromatogram. So the question is, what about all other peaks? Because we know that this is also palmitic, but how it can be that it's in such different places. And what we figure out that this peak, it's a free fatty acid, free palmitic, but for example, these 2 peaks of palmitic acid, in fact, are palmitics that were released from lysophosphocholine containing 16 carbons with no double bonds. And this makes a lot of sense also if we look into the polarity of those compounds, because free fatty acid it's quite non-polar, and that's why as a free form, it elutes as the last one here, but the presence of phosphocholine group increases the polarity of the whole molecule enough to make the retention time almost half from the free fatty acid. So the easiest way to deal with in-source fragmentation is to always go back to the chromatography, always to go back to the retention time. Talking also about the in-source fragmentation, I have to say that if you want to look for fragmentation spectra to compare with those formed in source, I would recommend to stick to those with 0, eventually 10 electron volts from methylene. Do not compare those with higher collision energies, with the higher energies, because they will never work. But at this time, I would like also to mention that coming from in-source fragmentation just to metabolites or lipids fragmentation, that it is highly important to consider the collision energies. As you can see here, based on the linoleic acid example, that the fragmentation spectra can differ a lot between different collisions energies. So planning your MS analysis, always try to predict which collisions energy you want to use. If you have no idea at the beginning, just stick to the numbers provided by the library. So either 10, 20, or 40 electronvolts, because in this way would be also easy to compare your fragmentation spectra with those available in the databases. Why this is important? Here I brought for you example of one oxidized phosphocholine, which was analyzed under lower collision energies and higher. And with 20 electronvolts, we obtain quite a decent signal for the head group, for the phosphocholine, but increasing this energy, we obtain even more fragments, we obtain even more structural information about the head group. But with lower collision energies, we could observe very clearly the signal corresponding to the water loss that clearly indicated that there must be some hydroxyl group there, and therefore pointing to the oxidation, which is quite important from biological perspective, while we are totally missing this information with higher collisions energies because we are basically over fragmenting the molecule. So if possible, especially in terms of lipids, try to fragment them with lower and higher energies, because each of them will provide you slightly different structural information. In terms of spectral matching, when we are comparing the fragmentation spectra, we have to remember that we must match the mass, but also the abundance of our fragments. I'm not talking about such obvious things like we have to remember that comparing MS spectra, we have to consider the type of mass analyzers, because they are different. We have mass analyzers performing MS in space or in time. We have to consider the ionization source, the collision energy, the type of modifiers we use. So those are, in my opinion, quite obvious aspects, but sometimes even very small differences in the mass can already give us quite important information about the structure of the molecules. Here we have a spectra for the same precursors, where both of them are dominated by the fragment 84, but in the one spectrum we have fragment 130, and at the other one we have 129, and there's only basically one Dalton difference between these two fragments, and it's already enough to make a huge difference in the structure of those molecules, because one is just glutamyl lysine and another is gamma glutamyl lysine, which again we are coming back to the same point that will affect our interpretation of our data, because the biological properties of these two molecules are different. But here I have an example when the spectra contains as two dominating fragments to the same fragments. In both cases, we have 79.9 and 93.3. I do not refer to other lower abundant signals, because very often in complex biological samples, we are missing them, or they are mixed with some noises. And this is an example of two molecules which have the same fragmentation pattern, but depends what is the proportion between different fragments. They will correspond to two very different, completely different molecules with very different properties. So this is also extremely important. To give you some lipid context, in terms of spectral matching, here's an example of HETE, hydroxyecosatetra enoic acid. We can find them very commonly in our samples. We are lucky and we can separate different isoforms of this molecule. We can have a quite clean spectrum where different fragments are present corresponding to different bits of the molecule, but depends what is the position of hydroxyl group. We can have a different isoforms. It might be 11, 12, 8, 3, 5, and it's quite important to determine exactly which form we are dealing with, because they are formed through different enzymatic systems, and therefore the interpretation of the data will be different. And here, although I have a mixed spectrum, I can see that based on some characteristic fragments, I can determine which isoforms I have in this case. Also, let me give you two short examples of lysolipids, because they usually are detected with two isoforms, SN2 and SN1, depends which phospholipase act to form the lysolipid from phospholipid. And if in terms of phosphoethanollamines in negative ion mode, if the fragment 196 it's more abundant than 214, we are talking about the form SN1. If it's the other way around, we are talking about the form SN2. Or I have another example from phosphoinositols, where if the fragment 153 is more abundant, then we have the isoform SN2. If those two fragments are more or less comparable, none of them dominate over the other, we can say rather that this is SN1 form. And also in reverse phase chromatography, SN1 elutes after SN2. SN2 always will have smaller retention time than SN1. So again, that's what we observe in the spectrum. If we are not so sure, because this is enough difference to say that this is SN2 form or not, we can always go back to the retention time, to the chromatography, and check which spectrum came from which peak, and then also confirm our findings. What is also important is that very often our chromatography, it's not sufficient to isolate, to separate some isoforms or isobars. It is because nowadays we have a tendency to short the method. So we are looking for high throughput methods where we can analyze as many samples in as short time as possible. Therefore, the chromatography is shorter and shorter, and therefore the resolution, chromatographic resolution of some isoforms is not enough. And keep in mind that your spectrum might contain information coming from different species. Like in this case, we have just two forms present in one sample, but for the same project, for another sample, we found that they in fact are three different coeluting forms, all of them corresponding to the same lipid, which is phosphocholine with sumeric number of carbons 42 and 8 double bonds. But depends which isobaric form we are talking about, the number of carbons and double bonds on each of the sides, it's different. Okay, I don't want to go today through the fragmentation of particular lipid classes, because this is quite nicely described in the literature, and you can easily follow different tables and guidelines that were already reported. Here are some publications that I can recommend. This Adipo Atlas from Maria Fedorova group, it's absolutely fantastic, and the supplementary file from this publication, it's the most frequently opened file on my computer. And there are also two tools thinking about a high throughput annotation as LipoStar and Lipid Hunter. Both of them are free, so I can recommend to use those softwares. Going back to the retention time information, first of all, we can have a different modalities of the HPLC used for our analysis. And first thing that we need to be really sure about is that we understand the mechanism behind the separation, because if that's not the case, we can not interpret properly our data. And there is one a very nice publication from Mike Lange and also from Maria Fedorova group, where different chromatographic modes were very, very nicely described, particularly in context of lipid analysis. So I encourage to read this publication, and as was proved, especially also in terms of lipids, depends which type of which modality we will use. They are obvious advantages and disadvantages of each of them, but still in the fields of lipidomics, reverse phase chromatography, it's the one that it's preferred. The easiest way to use in the high throughput way retention time information is to plot our M over Z against the retention time, and then we can see our chromatogram formed not by a continuous line but through the dots, where each dot corresponds to one lipid, and they are colored here by lipid classes. And this is the simplest way to visualize the data, and also the easiest and the quickest way to find find outliers in our annotation and also in source fragment, because if in the region here, the purple, we have phosphocholine, suddenly I see lysophosphocholine, that means that most likely this lysophosphocholine was formed by in-source fragmentation, and here is the fatty acid that corresponds to the other part of the molecule. Or here I can see that although M over Z increase quite significantly, my retention time is not changing. So probably this is some contaminant, some polymer that fragmented in source, and I should remove most likely those signals. Very commonly used in terms of lipids analysis are Kendrick's mass defect plots, which are very, very useful, and we can plot our lipids considering the number of hydrogens, which will reflect the number of double bonds, number of oxygens, so we can see oxidized forms, and we can visualize our data in many different dimensions, and we can see if the lipids follow particular trend or not. In this way, we can either find outliers, so basically one particular lipid was wrongly annotated, and this is particularly useful if we are using some automated tools for our annotation, or we can even annotate some lipids if they are still unknowns based on their behavior on these plots. We can annotate them. So this is very, very useful tool to visualize our data and to check if our annotations are correct. Moreover, retention time information can be used in the way that we are not focused that much on absolute value of the retention time, but rather on the elution order. This is a very nice example of a separation of different form of oxidized cholesterol esters, where different we have the same ion with the same mass corresponding to different isoforms, depends how particular molecule was oxidized. If that was epoxy, oxo, hydroxy, peroxyl groups, and so far and so on. And we can see that first of all, they follow particular elution order, but also we can put them into some pattern saying which forms will elute in which order. And in this way, we are coming to the elution order information, because LC, in contrast to GC, is not that reproducible in terms of retention time. Furthermore, the number of available columns, modifiers, mobile phases, and so far gradients, and so far and so on, makes basically impossible to use retention time for a direct comparison between different laboratories. But we can always use retention time order. So we forget about the absolute value of the retention time, but at least we want to know if some lipids are eluting in correct order. And we can apply these rules based on the carbon length of the carbon, so how many carbons we have in the chain, and also how many double bonds we have. So what is the level of unsaturation? Basically, the idea is very, very simple. More carbons, more non-polar molecule is. So if we have more carbons in our molecule, then the retention time will be bigger. How big will be the difference in the retention time? This depends what are the conditions that we applied. And in this way, we can easily find the lipids that do not follow this trend. And we know that, for example, most likely this one, it's a misannotation, because the retention time, it's too small for such big molecule. And we can apply similar rule to the levels of unsaturation, where more double bonds makes molecule more polar. So more double bonds, smaller retention time. So we can see that 16.0 elutes in this particular case in 16.2, 16.3 elutes in 15.1. And the same, we can use this information either to confirm some identification or to remove them. And we also implemented this functionality in serum mass mediator, and there is one quite nice, in my opinion, a functionality where you can put your masses that you want to annotate, the masses that you found statistically significant in one place, but also here you can put all other masses, all that are not significant. Usually we do not make use of them, but more lipids we will have annotated and put it in such pattern, forming such chain, more confident our annotation will be. So we will annotate the lipids, the masses M over Z that are here, but information that is provided here will be used to support those annotation. So I encourage you to try this functionality. The definition of identification and annotation is already known. I would like to highlight the fact that it doesn't matter if we are talking about the identification or annotation. This is a comparative analysis. So what does that mean? What is the implication of this? Our annotation is as good as candidates that we use for this annotation. And usually we think annotating our metabolites or lipids, we think that they are crude metabolites, that they are crude lipids, that this is just, for example, palmitic acid. But it might be that this is hydroxypalmitic acid or methyl or sulfate or phosphate. And we have to keep in mind that maybe the molecule that it's in front of us that we are trying to annotate, it's not a native molecule, not native lipid, but some biotransformed lipid. And here we can talk about epilipids, epilipidomics, which is quite nowadays quite fashionable term. In terms of those modified metabolites, there are two platforms that are the most interesting for such kind of approaches, My Compound ID and mine, which are using databases with native metabolites, applying different type of chemical rules to predict, to computationally generate some modified metabolites, to predict metabolites, but they are rather more useful for polar metabolites or metabolites other than lipids. In terms of lipids, I would recommend rather to stick to lipid maps and metabolomics workbench, where they provided a nice functionality for computationally generated lipids. Do you remember the building block concept? So imagine that to different basic building blocks, you put all possible combinations of fatty acids, and you generate based on this the list of possible lipids. Basically, this is what this functionality is doing. Also, what we have to consider is something that I mentioned before. The fact that something is not listed in the database doesn't mean that there are no other candidates. And in terms of lipids, it's quite easy to look for other options. Like for each PC, we can have a PE with 3 carbons more. And on the Lipidomics Standard Initiative webpage, there is a list of isomeric and isobaric overlaps, where you can see what can be the alternative identities, alternative lipid for particular lipid that you are dealing with. So for PC, we can have a PE with 3 more carbons. That's what I was telling before. For PC, we can have PE following this, that we have to add 5 carbons, double bonds, and ammonia adduct. So here you can find the list of different possible isomeric and isobaric options for different lipids. And I find this very useful in my annotations. But sometimes I see that, oh, obviously this is phosphocholine, but I don't have any candidates for phosphocholine in the databases. So in this way, we can sometimes come to some nice annotation. Once we annotated our lipids, we have to present them in the correct way. We have to name them in the correct way. And there are some very basic terms related to the nomenclature like SN, which is telling us what is the stereospecific number in terms of how the what is the substitution of backbone. Lyso, the prefix lyso means that this is monoacyl form of glycerophospholipids. O and P prefix corresponds to the ether lipids containing either alkyl or alkenyl ether substituent. And please, I saw this so many times that I have to highlight this. If you have on the list of the candidates from the database, for example, lyso-PC, lyso-PC-O something, lyso-PC-P something, each of these candidates is a different molecule. You cannot put the sign, the symbol of equal between lyso, lyso-O, and lyso-P. No, each of them is a different molecule, and each of them must be considered as a different molecule. For ceramides, D and T for sphingolipids corresponds either to D or 3-hydroxyl long chain bases. I was mentioning today, sometimes I was using word isomers or isobars. This is quite important. If we are talking about the isomers, corresponds to two molecules where the position of fatty acid chains on in the backbone is it's different. So depends either if one or the other fatty acid is on SN1 or SN2 position, we have two isomers. But very often we are dealing with isobars, which means that isobaric molecule to either this or this one, it's another one which contains the same summarically the same number of carbons and double bonds, but those carbons and double bonds are distributed between these two chains in a different way. So this is quite important to distinguish the difference between them. Very quickly, because I already talk for 1 hour. In terms of lipids fragmentation and which fragments provide us which information, we can have fragments that are characteristic for, that are lipid class specific fragments that will be either fragments themselves, like 184 for phosphocholine in positive ion mode, 241 for phosphoinositols in negative ion mode, or neutral losses. So that's what we observe as a loss, the loss of 141 to identified phosphoethanolamines or 185 for phosphoserides. We can have also lipid molecular species fragments, which will provide us information about the fatty acid composition, and depends about which lipid class we are talking about. We can either look for them in the positive or negative ion mode, although as a general rule, fatty acids are better detectable in negative ion mode. Putting these two pieces of information together, we can provide information about our lipids. And I would like to, for a moment, focus on these two examples, because there are two different lipid classes, but in one case, I used the slash to separate the two fatty acid, and in another case I use underscore. What is the difference? The difference is huge, and I want you to be aware about this. According to the rules included in, I think, 2020, if we know exactly the position of fatty acids on our molecule, we are using the slash. So this name means that this is a phosphocholine with 16 carbons with no double bonds on SN1 position and 20 carbons for double bonds on SN2 position. While in this case, we only know that the molecule contains two fatty acids, one 16-0, another 18-1, but we don't know how they are connected to the molecule, which is on which position, which is on position SN1, which is on position SN2. This is quite important, and please try to follow those recommendations for lipids nomenclature. The class-specific, lipid class-specific fragments are provided in many different publications. They are also very nicely summarized on the Lipidomics Standard Initiative webpage. Those of you who are working with lipids must be familiar with this initiative. So I highly encourage you to go there and to check what they are doing. And they have lots of educational materials on the webpage. So please go there and check it. For positive ion mode, for negative ion mode, they have also lipid molecular species-specific fragments, so the fragments that are telling us what is the composition of fatty acids. Then there are also some other classifications. Basically, they follow the same idea. They have slightly different name and another level of details, let's say. We have lipid class selective fragments, which are lipid class specific fragments according to another classification, molecular lipid species specific fragments, and double bond location specific fragments. These are not so frequently used because if you are using lower collisions energy, you will not always see such information in your MS spectra. But regardless, if you will follow the previous classification or this one, it's nice if you will indicate which fragments corresponds to which class. Now, this publication prepared by Gerard Liebisch and other people by collaboration with Lipid Maps from 2020. It's one of the most important lipidomics publications in the last years. Please, if you don't know it yet, check it. They provided absolutely fantastic and really detailed and profound explanation about different levels of annotations and how to turn these different analytical information into correctly presented names of the lipids. So here I have two examples for fatty acid and for phosphocholine. Maybe because of time I will jump to the second example. We can sometimes we do not have enough information to say exactly what is the composition of fatty acids. For example, in positive ion mode, we know only that this is a phosphocholine, and based on the mass, we can say that it contains 36 carbons and 4 double bonds. If this is the only thing we know, this is how we should present our results, and no one will complain about this. Maybe we know what is the composition of fatty acid, but we don't know how those two fatty acids are distributed in the molecule. If we know, we can put that this one is on SN1 position, this one on SN2. Maybe we have information about the double bonds, then we can say it. Maybe we have even the information about the geometry of those double bonds. Then we can provide. But what is the general idea? Only report the information, other way around. Report the details that you can prove with the analytical information you have. Don't put, it doesn't matter that the database told you that this is PC 24160. No, the database doesn't know the information you have. So if you don't have composition of fatty acid, just put sum the carbons and the double bonds and report it in this way. Report, provide only the name with the details that you can prove with your analytical data. No more. But here we are coming to a kind of problematic situation, because from analytical perspective, we should, and for annotation, we should only provide the information we can prove, only the information we have based on our analytical evidence. But from the biological perspective, for the interpretation of our data, the name of metabolites, the names of the lipids should be as precise as possible, because in terms of lipids, let's just look into omega-3, omega-6. They will have very different biological properties. In terms of, for example, here I have hydroxyproline. Depends if it's 4 or 5 hydroxyproline, it will have a different properties. Depends if it's symmetric or asymmetric dimethylarginine, the same story. So we have to find a compromise between how to interpret our results in the best way, but at the same time, how to present the results of our work, because finally, this is analytical work in the way that it's robust, it's trustful, and it really reflects the information we have. So try annotating your lipids, try always to put on the table all possible sources of information. If you have ion mobility, fantastic. Cross sections are absolutely amazing for lipids, especially isomers. Maybe you have ontology information, sometimes using information about the origin of the sample or the disease, or from which organ or which type of cells you have the extract will be also very useful to maybe if not confirm, at least to reject some of the possible candidates. Put all the information that you have on the table and play with this data, going back and forward, going from MS to retention time, from retention time to MS/MS, from MS/MS again to retention time, trying to make your annotation as confident as possible. Finishing, I would like to again thank you, Vinicius, for invitation for this nice initiative. And as I believe we have here people interested in analysis of lipids, I have to take an opportunity to advertise EpiLipidNet, the cost action that I'm quite actively involved in. We have still 2 years of work going on, so I would like to cordially invite all of you to visit our webpage and to join our activities. We have 5 working groups which are devoted to very different aspects of lipids analysis, covering analytical aspects, clinical aspects, computational aspects, trying to address such issues as problems to place some lipids in the metabolic pathways because they don't have identifiers. So we have a lot of different and very nice initiatives. We are organizing a lot of online meetings and webinars, also some schools and in-person meetings. So anyone who is interested in joining us or participating in our activities, please feel free to visit our webpage and to contact us. And last but not least, thank you very much for your time and attention. And if you have any questions, I will be more than happy to answer them. Of course, as long as I know the answer.
Great, Joanna, thanks a lot. You did not reach the expectations, you overcame them. So it was very informative, really, as always. And I have a list of notes, questions, comments, but I also, of course, want to give the space for the others. So like I mentioned at the beginning, let's do like that. If you want to send your question via the question and answer, you can just write it there. Otherwise, it would be nice if we have an interactive session. So just raise your hand and I can allow you to open your mic and camera. I guess the camera should also be allowed, I hope. Yeah, but sure. Then you can ask the question. So in the meantime, while people start to write or raise the hand, I will start. Let me pick what I want to ask first. Maybe let's start with the different levels of confidence that you mentioned, because as you mentioned, for sure, it's difficult to have always standards for all these lipids. And it's just too many layers, because first you have to know what are your fatty acid chains. Then you need to know if there are double bonds, where those double bonds are, and if they are cis or trans. So it's just too many layers. So from your experience, not only in your work, but also what you see out there, how precise normally is this identification in people doing lipidomics? So let's say, would you say 1% of the lipids are fully identified? I mean, you don't need to say a percentage, but on your experience.
I would say, depends what is the aim of your study. If you want to just present an overall lipidome change in some particular disease or some particular case, those identification don't have to be very precise, and furthermore, they cannot be very precise, because if you are performing untargeted lipidomics, simply you cannot reach some of the details. furthermore, even if you can buy some standards, like you can purchase 1,000 standards with many different options about the composition of fatty acids, cis trans, blah, blah, blah. In many cases, you are not even able, with given chromatographic conditions, to separate those lipids. So what you measure is the cumulative amount of lipids, for example, in terms of where the double bond is placed or how it's placed. Yeah, I would say that this very detailed information are crucial if you are performing really targeted or quantitative lipidomics. But then anyway, you need standards. Yes. So and this is usually when you target some particular lipid route, when lipid path where you want to track some changes among lipids involved in one particular pathway or one particular process. And then yes, you have to be sure about the isoforms or isobars that you are using. But in all other cases, I would say that also depends, like if you want to present the whole snapshot of lipid, very often you put a lot of effort to identify your lipids, but finally there is no way to interpret those data going lipid by lipid, because as I mentioned, there is a huge problem with lipids in terms of the pathway analysis, because to place something in the pathway, you need to have identifier. You need to have either HMDB number or KEG number, some kind of number that will, because in the pathways we are placing those identifiers, yes? So in terms of lipids, maybe 10% of phosphocholine have identifiers, all others not. But do that mean that they are not important? No. And very often with Javier from Symbio, we were discussing lipids from the concepts of trees and forests. If you are approaching particular disease from a lipidome profile for the first time, more important for you will be to know what is this forest, which types of trees are there, what is proportion of which of types of trees. You don't care about single tree. But if you are really deep into one particular clinical problem, you already know that, I don't know, arachidonic acid pathway is disturbed, and you want to see exactly which level, up to which extent, then you are interested in trees, and then you will look for standards. So you can find many different levels of confidence in lipidomic studies. I would say that in untargeted studies, usually you have the mixture of different levels, that you will have, maybe some of the lipids were identified only in positive ion mode and there is no information about the fatty acids, other, yes? So there's a mixture. Or maybe some of them you annotated based on the ionization and adducts formation, then you will put level 3, yeah? So you can mix them, and I would say that demand to stick to one particular level of confidence is rather a function of what is the aim of your study, and not as a general requirement or general recommendation for the field.
Yeah, great, thanks. Just to know, because sometimes I see raised hands that already go down, please write in the chat then if you want to make a question, and I will open the mic, because I'm not sure if people are just shy that raise the hand and then give up, or yeah. So please write also in the Q&A. So in the meantime, I'll also make another question. First of all, I also liked a lot your example on the palmitic acid and the in-source fragmentation, because it's also something that I don't think many people look at it. And it's also funny that these days I'm using here SCIEX instruments, and even in MS1, you have to add a collision energy. So there's a parameter there, and SCIEX recommends that at MS1 you use like at least 10 or 12 as collision energy, because they say that if you don't give this push to the molecules, you may lose sensitivity. Yeah. And that's a value that they claim that it's low enough to not lose sensitivity, but also not to fragment your molecules, which that's true. I'm not really sure that's the case. So it was a very interesting thing to see.
I can tell like this, from my experience, there is no way to avoid in-source fragmentation. It doesn't matter how soft your conditions in the ion source will be, the ion source fragmentation will occur always. We were trying to really limit this parameter really going really down. We were testing this both on LC and on capillary electrophoresis, and even going to the values lower than 100 volts, we still were observing in-source fragmentation. So I would say it's impossible to avoid it, but if we cannot avoid something, let's make this thing to work for us. So you can add the information about particular fragments that usually appear as an in-source fragment or neutral losses. You can basically add this to the list of your expected ions and try to deal with this during the data reprocessing step, or you can use this even for the identification purposes. Sometimes there is not enough sample available or not enough time on instrument to run MS. You can run just few samples with intentionally increased collision energy, then just use correlational analysis to confirm either if particular fragment originate from particular precursor, and that can quite nicely work for the identification purposes. So if you cannot avoid something, let's make this drawback to work for us.
For sure.
Yeah.
Okay, so people are shy apparently, but I will still make some questions because maybe it's also something that people want to ask and are just shy to ask. But coming back to the collision energy, because you were also mentioning the difference between using 10 electrovolts or 40. So normally in your approaches, you're normally acquiring two. First of all, I suppose you're doing DDA, or later you are just targeting the lipids that you find significant.
Yeah, in terms of lipidomics, there are two approaches. You can either follow the classic untargeted route when you are just analyzing your lipids on the scan level. You are performing statistical analysis and you are going back to the lab to target only the molecules that you selected. Yeah. But what is very common for lipids analysis is to perform DDA. And to annotate as many lipids as possible based on the fragmentation patterns, and to work only with annotated lipids. First strategy can bring you new information. Also, you can identify the new lipids that are not in the databases yet. The second strategy is more robust, faster, and let's say, from statistical perspective, it's more efficient because you are dealing only with the signals that are true lipids, and that makes everything easier in terms of the false discovery rate and so far and so on. But yeah, in terms of the collision energies, if I don't have time to run my analysis with two different collision energies, I will go for ramped collision energy, where the collision energy is calculated for particular mass, as a function of the mass. So bigger molecule, bigger collision energy, more charges, smaller collision energy. But if possible, if I have enough sample, if I have enough time on instrument, or I have some lipids that I couldn't identify and they are the most significant one, then I will try to analyze them under different collision energies, because in some particular cases the fragmentation can change drastically from 10 to 30 or 40, and especially if you are struggling with annotation of some lipids, I would recommend to run MS with different collision energies. But in majority of the cases, this ramped collision energy, where the collision energy is automatically adjusted to the mass of the molecule, usually it works. Of course, there are some exceptions, like lipids containing a round of rings and so far and so on, that maybe the energy will be too small, but in majority of the cases it works pretty well.
Yeah, that was going to be my final question. If you acquire two spectra, or if you use the ramp normally. Okay.
If I don't have time for more analysis, I will use ramped.
Yeah. And for the adducts, because as you also mentioned, there are many lipids that ionizes better not with in the protonated form. Is that when you have the mass of those lipids with different forms that not the protonated, is it easy to find a match with the mass spectra? Because I suppose most of the databases contain normally the N+8, isn't it?
Yeah, for some lipids, you will never find a MS spectra for protonated or deprotonated form because they never form such ions. Like you will not find such ion for deprotonated for phosphocolines, or I don't know now. Protonated for phosphoinositol. If you will measure phosphoinositols in positive ion mode, they will be rather ionized with sodium or potassium. But in turns, in negative ion mode, they give an absolutely fantastic signal through the deprotonation. In some cases, I think that your question rather correspond to those lipids that can form several different
Yes, exactly.
adducts. And from my experience, the fragmentation spectra can differ a lot. I mean, the fragmentation is the same, basically, but because of the presence of very different adducts, because there is a huge difference if you have proton with the mass 1 Dalton, or if you have as heavy adduct as sodium or potassium. This is changing the molecule quite a lot. So the fragmentation will be the same, but the fragments that you will observe will be different. Nowadays, there are few publications focusing on the annotation of lipids ionizing with different adducts. One of them is also our publication from Senvio, where we found that suddenly, for example, for phosphocholine in positive ion mode, you observe several neutral losses. That it's like, come on, what is this? And this is quite characteristic if the ionization occur with something else than proton. And this is quite problematic in terms of the databases because they will contain the most common, the most frequently occurring the adducts, and then basically what I'm doing at such case, like if I know the fragmentation pattern, I will basically draw my molecule, break it into fragments, add another type of adduct and check old school. Yeah, old school. Yeah, but the good point is that nowadays also this problem or issue is very commonly addressed in different software. So they are also considering this, and this is definitely helping in the annotation.
Great, Joanna, thanks. So far, no questions. I hope people can raise their hand or type in the chat. I'm afraid somehow I blocked everyone. Hopefully not, but in any case, before I ask my last question, then I would just like to highlight that Joanna put herself open to receive questions later. So as you can see in the screen, there's her email on the corner. So if you are shy or just have a question later, you can get in touch with you.
There is something happening in Q&A, I see.
Yes. Okay, so it is working.
If you see this, the chat will work. Okay.
It's just a test. Okay, so it's working. All right, thanks, Max. No, but then my final question, Joanna, for you is, have you got an experience or at least heard about the new technology that SciEx is launching now with the Zenith of the EAD?
Oh yes, on lipidomics meetings, this is
what everybody's talking about. And I think it's too early because we got this instrument recently and we had the training with SciEx, and it's a new technology, so it's normal that not even then know all the ways yet, but it seems very promising for lipid identification because it's, I don't know if I can compare with something. It's like having an electron impact in GC where you just fragment everything and you can see all the small fragments and basically see where your double bonding is and things like that. But of course, it is still unclear. But my question would be if maybe in the future, when more information comes, if this would be something that you would pursue to add in the cell mass mediator for lipids, if you foresee this.
My first thought about this new technology is that I really do hope that that we can follow with the software, we can follow the hardware, because very often what I observe in general in the field of metabolomics, lipidomics, or mass spectrometry is that we produce quicker, very nice machines that can produce absolutely amazing data, but we cannot make a true use of this data.
We don't know how to deal with it.
Exactly. So if we will not have a software that in high throughput manner can make a use of this information, in fact, it will be nice to have this this added value to the data, but we will be not able to make a true use of it. So the first thing is that hopefully together with the hardware, we will have some software, some tools to make a true use of this data. And of course, we are still working on cell mass mediator. I'm not that actively involved since I left Madrid, but they are still working on cell mass mediator. And I think that if there is something that can be automatized, I mean, even if you are doing something in the repetitive manner, following some rules, that means that that can be automatized. And if something can be automatized, I'm very sure that it's just a question of time to implement this to the platforms such as cell mass mediator. So yeah.
Great. So yeah, thanks again, Joanna. I can tell you how glad I am that you have accepted the invitation, how nice this was. And yeah, hopefully we'll have more contributions later, or collaborations, let's call it like this.
Sure.
Between our two
Thank you very much for invitation, for having me here. It was a real pleasure. As Vinicius mentioned, now I'm sending these words to all our attendees. If you have any questions, any doubts, any ideas, or something that I can help you with, please do not hesitate to contact me. Just drop an email, and I will be more than happy to answer your questions. So thank you very much once again, and good luck for everyone fighting with lipids.
We need it. Thank you again, Joanna.
Thank you.